Welcome everyone. Today's lecture will be on the thermal resistance concept for cylinders. So if you look at the paper, we will get started. Okay. If we start with Fourier's law of conduction, we know that what we have here is the heat transfer rate can be calculated from minus K, the thermal conductivity, the area, times delta T, delta R. We're here again, we're talking about a cylinder. So our area would be the surface area. So we're talking 2 pi times the radius times the length. Okay? And as far as the geometry goes, we'll start with something like a pipe first. Call this radius here R on the inside, and we'll call this radius here R on the outside. Okay. Now the length here, this is like coming out of the page. Okay. So like in 3 dimensions, the length would look like this. Okay. Now if we substitute the area into this equation and separate terms and integrate, we'll get this. And what we want to do is integrate from R on the inside to R on the outside of the pipe. So we'd have Q dot divided by the area, 2 pi L K, or 2 pi L times R. Sorry about that. And then here again, if you take the K and divide it through, you have a K here. Okay. Now all of this is going to be times delta R, and that's equal to delta T, the temperature drop. Okay. So all we did was take this equation here and substitute it for the area, separated terms, and we're going to integrate from R on the inside to R on the outside. And the temperature here would also be T on the inside divided by T on the the limits of integration would be T on the inside to T on the outside, where obviously this is T on the outside and that is T on the inside. Okay. So if you perform this integration and do the math, do the algebra, what you would see is that Q dot is equal to 2 pi L K, the thermal conductivity, times T on the inside minus T on the outside, divided by the natural log of R on the outside divided by R on the inside. Now here again, we're assuming the heat transfer is going from high temperature to low temperature. So we'll just say Q dot's going in this direction, which would obviously mean that the T on the inside is hotter than T on the outside. And here again, that's why we have the negative K here. Alright? So with this equation here, we can go back to our definition for resistance. And if you recall, the resistance, just physically, is equal to potential divided by rate. Okay? So if we go back to this picture, what do you think the potential would be? In other words, what is driving this heat transfer, the Q dot? Well, that potential is going to be your temperature drop. So here again, the potential is T on the inside minus T on the outside. And just like with the plane wall, the rate, of course, is going to be Q dot. Okay? So if we take this equation here and solve for potential divided by rate, which would be our delta T divided by Q dot, what you would have left, if you did the algebra on that, you would have the resistance due to conduction for a cylinder, and that would be equal to the natural log of R on the outside divided by R on the inside divided by 2 pi, the length of the pipe, times the thermal conductivity. Okay? So that is our thermal resistance for a cylinder if we're talking about conduction. Conduction. Okay? So the other thing we would have is convection. Alright, so if we start with Newton's law of cooling, we know that we have Q dot is equal to H, the convection coefficient, times our area, times delta T. So if we plug in for the area, we'll have H 2 pi R L. And the temperature drop here, I'm going to say, is T on the outside of the pipe minus T on the outside infinity. And here again, this is Q dot due to convection. Now if we go back to our picture here, T on the outside infinity will be out here somewhere far away from the surface, and similar to that, T on the inside infinity will be somewhere towards the center of the pipe. Okay? So what's driving this convection is our potential here, which is T on the outside of the pipe minus T on the outside infinity. So here again, resistance due to convection is equal to potential divided by rate. And if we're talking about convection, that potential would be T on the outside minus T on the outside infinity divided by rate again, which is Q dot. I'm going to call it Q dot convection. Okay, so if we solve this equation here for delta T divided by Q, what we have left is that R of convection is equal to one over H times the area, which is 2 pi R on the outside divided by L. And that's the resistance due to convection on the outside of the pipe. We can do the same thing on the inside of the pipe, and R due to convection, I'll get a subscript of I for inside, and this one O for outside. So the resistance due to convection, the thermal resistance due to convection on the inside of the pipe would be 1 over H on the inside, 2 pi R on the inside L. And here again, this convection coefficient on the outside we'll give it a subscript of 0 because it will be different than the convection coefficient on the inside of the pipe. Okay? So here again, with these types of problems, this thermal resistance concept, we're talking about one-dimensional and steady flow. Okay? So let's say we'll look at a geometry here. I'll just draw part of the pipe. Now see, you may have several materials here in series. This may be the pipe itself. This may be the insulation that's on the outside of the pipe. Okay. We may have some liquid, maybe steam on the inside, maybe air over here on the outside. So how many resistors would we have? Well, we'll have a resistor due to convection. We'll have a resistance due to conduction through the pipe. And then we will have a resistance due to conduction through the insulation. Then one more, a resistance due to convection on the outside of the pipe. So we can connect all these. And what you would have, let me redraw it down here. Here we would have T infinity on the inside, a resistance due to convection on the inside. We'll call this arbitrarily, we'll call that T on the inside. We'll call this T1. We'll call that one T on the outside. This one T on the outside, infinity. We'll arbitrarily call this R1. We'll call that one R2. Both of these are due to conduction. One for the pipe and one for the insulation. And over here we'll have R convection on the outside. So since these resistors are in series, we can add them all up to get an equivalent resistor. Tell you what, let me turn my paper this way. Plus the natural log of, I'm going to call this R on the inside, R1, and R2, and then R on the outside here. Like this. So we'd have the natural log of R2 divided by R on the inside divided by 2 pi LK plus the natural log of sorry about that, the natural log of R2 divided by R1 divided by 2 pi LK. And then one more would be 1 over H on the outside, area on the outside. So with this thermal resistance concept, we can calculate our heat transfer rate Q dot, which would be T infinity on the inside minus T infinity on the outside divided by R equivalent. Okay? So here again, if we had a pipe with insulation, we got Q dot, and we can calculate the heat transfer being lost from that pipe. Okay, that concludes today's lecture. I'll see you next time.